Welcome to CMOS RF integrated circuits. Today we are going to carry on from where we left in the previous lecture, and we are going to start with the first cut at an oscillator. So, in the previous lecture we saw, we are now discussing oscillators, just by the way, right. So, the first thing that we saw was most basic oscillator is inductor and shunt with a capacitor, and never will you get an inductor which is a perfect inductor. It will always be an inductor in series with some resistance because of the resistance of the wire. Then there is going to be eddy currents, etc., all that stuff you can lump into some form of a resistance, right. And inductor in series with resistance can be transformed to inductor in parallel with resistance. So, I am basically lumping it as an inductor in parallel with some resistance, and this is the most basic form of a tank, and this is the most basic form of an oscillator. Unfortunately, this will never oscillate. So, to make it oscillate, what I am going to do is I am going to create some sort of a minus R and put it in shunt with the entire tank. So, that is my plan, right. This is the most basic form of an oscillator. We also picked our brains and we reminded ourselves that there exist other forms of oscillators as well, ring oscillators. You can even design your own one with poles on the j omega axis or outside on the right half plane, right. So, it is possible to do such stuff. You can also go for a different class of oscillators. So, there exists a second class of oscillators called relaxation oscillators. Okay. You might have studied in the long past, you might have studied IC 555 timer, yeah, bistable multivibrators, yeah, maybe you have studied such stuff, right. So, those are relaxation type oscillators. The theory for relaxation type oscillators are very different from the theory that we are going to study. It is very different, okay. Does not work the way we look at it, right. So, for relaxation type of oscillators you usually use some kind of a, so I will just draw an example of a relaxation type oscillator. So, I am going to use a Schmidt trigger. So, some sort of schematic like this might work as a relaxation based oscillator. Okay. Might have studied Cedra and Smith or old microelectronics book which talks about bistable multivibrators, right. The theory for these kind of oscillators are very different. Why? Because of this particular block. Almost always you are going to use something like a Schmidt trigger, and a Schmidt trigger is not really a time invariant circuit. Schmidt trigger, when the voltage is rising, has some characteristics, when the voltage is falling, has some other characteristics. So, the system is not time invariant, the system is time varying. So, because of this property, the theory for this kind of relaxation based oscillators is very different, and we are not going to study it, at least not here. Okay. So, let us first attempt to make a tank based oscillator, and as we talked about it, if I merely put an inductor in parallel with a capacitor, it should work, but I understand that the inductor is never going to be an ideal inductor. So, there is going to be some parasitic resistance So, this is unintentional, this resistor that I have drawn is unintentional, that is why I have put the dashed line over there. It just so happens that it is there. Now, what do we do? Our plan is to put a minus R in shunt with the whole damn thing, right, and hopefully this is going to work. Now, you are going to say that what is this minus R block, where do I find such a thing? Now, our savior is the latch circuit. I do not know if you recall ever having used such a circuit. Might have used something like this. Even if you have not used, let us check it out. Okay. So, let us analyze the latch circuit. This is called the latch, or it is called the cross coupled pair. Okay. Let us just analyze the latch circuit, the cross coupled pair first. Let us say that differentially I apply a signal of plus V by 2 on this particular node and minus V by 2 on the other node, all right. And the question for you is, what is the impedance that I see looking into this circuit? So, from these two ports, what is the impedance that I see looking in? Or in other words, what is the current that is produced by the plus V by 2 voltage source, and what is the current taken by the minus V by 2 voltage source, right. We have to find out these two currents, and that divided by V by 2 is going to give me the resistance, all right. So, let us do this first. So, the voltage here is V by 2, the voltage at the gate over here is V by 2, voltage at the gate over here is minus V by 2, and let us replace the MOSFET with its typical small signal model. The small signal model of the MOSFET is that I am going to use for now. is this. Okay, this is the typical small signal model of the MOSFET. I have thrown out all the capacitors conveniently. All right. So, let us throw out all the capacitors. It is really not good in the at radio frequencies, you have to consider the capacitors, but I have thrown them out just for convenience in our analysis. At least as far as DC is concerned, we will get the right result. In addition to DC, we are going to get some parasitic capacitors here and there, etc., etc. But our primary concern here is DC, right. Our primary concern here is in fact the resistive part of it. So, that is why I have conveniently thrown out all the capacitors. All right. So, let us replace the MOSFET with its small signal equivalent model. All right. So, this is what I have got as far as the small signal equivalent model is. This is RDS, RDS. Now, the values of the current sources, this is something that is important. All right. So, the one on the left hand side is minus Gm times V by 2, the one on the right hand side is plus Gm times V by 2. These are the two values of the current sources. And now, let us do Kirchhoff's current law to figure out what is the total current over here. And it is easy to see that what I have got is V by 2 divided by RDS, that is the current going through the resistor, minus Gm times V by 2. So, that is your I, let us call it I plus. Okay. And let us call this I minus, I am going to change the direction over here, I minus. It is interesting to see that I minus is going to be the exact opposite of I plus, which is something that is nice. Okay, which means that if I had put the other direction for I minus, then no current goes into the ground. This current is 0, which is wonderful, right. So, then what do I have here? I apply a plus V by 2 somewhere and it is taking a current I plus. So, what is the resistance looking in? So, the total voltage that I applied across these two nodes is V. So, I have applied V voltage and I plus goes in and comes out, right. So, what is the resistance? So, I apply V voltage, I plus goes in and comes out, means that the resistance is V divided by I plus. And all the V's cancel out, and what I have over here is something like this. Okay. Now, the good news is that if you have got any kind of a good transistor, then typical values of GM are going to be much larger than 1 by RDS. That is how you get gain from a transistor, right. GM times RDS has to be somewhat large, something like 20 or so. So, GM is going to be larger than 1 by RDS. Now, that automatically means that this quantity in the denominator 2 divided by minus GM plus 1 by RDS, this quantity in the denominator is negative. If the quantity in the denominator is negative, I have created something which has a negative input resistance. Wonderful, is not it? This is exactly what you are looking for, right. Now, when does this work though? It is just one catch over here. The catch is that you have applied a plus V on one side and a plus V by 2 on one side and minus V by 2 on the other side. Only then it is working like a negative resistor. So, differentially speaking, it looks like a negative resistor. If you apply a differential signal on both sides, then it is looking like a negative resistor. Okay. What happens if you apply the same signal on both sides? So, let us say I do this. This is my circuit, these are the two ports, and the point was that if I apply a voltage across these two ports, then I see a negative resistance. If I apply a voltage from these two ports with respect to ground, what do I see? That is the next question. It is very interesting. So, this voltage is V over here, this is V over here, this is also V and this is also V. Okay. And when you replace the transistor with its small signal equivalent model, what you get, I mean it is easy to reduce this whole circuit into just this. Two devices now. Okay. Two devices means looking in over here, the resistance that you see is going to be 1 by 2 GM. Approximately. You can shunt it with your RDS. Okay. So, that is the impedance that I see. So, now if I look in, I am going to see half of 1 by GM in shunt with RDS. Okay. Earlier what I was seeing was basically twice of minus 1 by G m in shunt with RDS. That is what I was seeing earlier. Now I am seeing something else. So, the resistance, the input resistance of this particular circuit depends on how you apply the signal. Okay. Suppose you apply your signal like this, okay. Suppose you apply your signal like this, then you are going to do some sort of superposition trick to figure out what is going to be the current. So, as far as VCM is concerned, the common mode voltage VCM is concerned, the resistance that you are going to see is 1 by Gm in shunt with RDS divided by 2, because there are two such things. As far as the differential voltages are concerned, you are going to see a different input resistance, right. You are going to see a negative input resistance as far as these two differential signals are concerned. As far as the common mode signal is concerned, you are going to see a positive resistance. It basically looks just like a diode connected MOSFET. Fine. Great news, because this is something that I like. I can put this MOSFET pair in shunt with my tank and I am done. Looks like I am done, just that I am not. This works when you think about the small signal. What about the biasing of this? These devices need to be biased, right. Should not forget the biasing of these devices, and if they need to have any kind of GM, they need to have some DC current going through them. There has got to be a power supply. So, supposing I need some current like this as far as DC is concerned, how am I going to create a current like that? So, one opportunity is that instead of having the inductor over there, why do not I delete this inductor from this place and place the inductor to the power supply on both paths. So, this is one possibility, right. This is something that a lot of people would like to do. Okay. So, as far as the differential mode picture of this entire circuit goes, so as far as the differential mode picture of this entire inductor capacitor resistor combination goes, this is what you have. Actually, the resistor does not appear there. this is what you have, right. I mean this is the circuit that you have, and looking in from here I see an effective resistance which is really negative, and the value of that resistance is something like minus 1 by 2 by Gm. Okay. So, now if you want to break this into a differential mode half circuit, then suppose this is R, this is L, this is L, this is R and this is C. How do you break it into a differential mode half circuit? First you have to break the cross components. So, the cross components can be broken into series components. So, you place two capacitors of size 2C each in series with each other, and as far as this negative resistor is concerned, you treat it like two resistors, two negative resistors, each of size minus 1 by Gm. Okay. Is it just minus 1 by Gm? No, it is not just minus 1 by Gm, there is also the RDS portion of it, that also can easily be broken. So, this is what I have to start with. All right. And the idea of the differential mode half circuit is that when I apply a circuit on when I apply plus V and minus V on both sides, it is like a seesaw and the fulcrum point is in between, which basically means that if I draw a plane through the axis of symmetry of this circuit, then all points lying on that plane will be at 0 potential, right. That is the way we transform a full circuit into a differential mode half circuit. So, using that concept, what I end up with is this, and if you redraw your thing, then this is what you have got. All right. Now, it is easy to see that when minus 1 by Gm is exactly equal to R parallel RDS, all you are left with are the inductor and the capacitor. The negative and the positive resistors, when they are in parallel with each other, they nullify each other, right, in this fashion. This is how they nullified each other. It is almost like there is an infinite resistor in shunt, which is nothing in shunt, right. And you are left with a pure inductor in shunt with a pure capacitor. Agreed? When you have a pure inductor and a pure capacitor in shunt with each other, the poles of the system lie on the j omega axis. You have got two poles, each pole is at what frequency? Minus 1 by square root of LC, 2 LC, in our case. Fine. And if you have poles on the j omega axis, then that means that your system is going to oscillate at that particular frequency. So, all this is wonderful. What this is not doing, there are two problems with this. Problem 1 is that how do I make minus 1 by Gm equal to R parallel RDS. So, this happens when 1 by Gm is equal to R parallel RDS, right. How do I make this equal? This is problem 1. Problem 2 is when the poles on the j omega axis, fine, the system oscillates at a frequency of minus 1 by square root of 2 LC. What is the amplitude of this oscillation? Is there anything that is telling me what is the amplitude going to be? Anything in my circuit that is deciding what the amplitude of my oscillations are going to be. We have done some small signal analysis. We have figured out the small signal input resistance of the cross coupled pair that happens to be negative, right. Is the amplitude also going to be small? Because if the amplitude is small, then it is bad news. What is this amplitude going to be? That is the second question. First question is 1 by Gm is equal to R parallel RDS. This is a very hard condition. First of all, R is something which I can only estimate. I never really know exactly what R is going to be when I am designing the circuit, right. I mean, I can tell you that if you make an inductor on an integrated circuit, the inductor will probably not have a quality factor more than 5, but that is not telling you much about what exactly the parallel resistance is going to be equal to, right. So, this is problem 1. Problem 2 is RDS. RDS is also a big unknown. When the process engineers create a semiconductor technology, they in general are not that worried about RDS, and the tolerances of on RDS, the exact value of the RDS could be as large as 200%. So, there is no control over here, and as a result 1 by Gm equal to R parallel RDS, this is a very hard condition to satisfy. So, the next thought is as follows: what happens if 1 by Gm is not just equal to R parallel RDS, 1 by Gm is this, less than R parallel RDS. I probably can't guarantee that 1 by Gm is going to be equal to R parallel RDS, but maybe I can make Gm large enough, maybe I can make Gm large enough, I can always make Gm large, I can make Gm large enough to drown out R parallel RDS. Is it possible to do that? Yes, it is possible to do that. What happens in that case? What are you going to see? So, you have got a negative resistor in parallel with some positive resistance, let us call it R prime. Okay. And So, what I am saying is let us make GM large enough, let us make GM very large. If I make GM very large, then GM times R prime is going to be more than 1. So, all I am planning to do is make GM times R prime more than 1. If GM times R prime is more than 1, then the quantity in the denominator is more than 0, that is it is positive. If the quantity in the denominator is indeed positive, then I have got a net negative resistance. Some negative resistance is what I have got. So, what I am going to do is I am going to make this GM times R prime much larger than 1. As a result, I am going to have a net negative resistor. So, that means that my small signal picture is going to look like this, small signal differential picture. So, let us call this entire thing R double prime. What happens here? What kind of a system is this? I have got a negative resistor in shunt with an inductor and a capacitor. What do you expect to have? What's your expectation from this kind of a system? Well, if you do the analysis, let's just do some sort of an analysis, right? Let's find out where the poles are, or what do you want to do? Let's say this is V, voltage V, okay, and I am going to find out if I apply a voltage V, what is the current I that goes in. Let us say that is what we are planning to do. Okay. So, this is clearly V by j omega L. Let us not use j omega, I am going to use S. All right. So, if I plan to look at the input impedance, this is what I see, which I can simplify a little bit. I do not need to simplify too much, just going to multiply the numerator and denominator by S times L. And this is what I am going to see. So, you have got a 0 at S equal to 0, which is okay, but you have got poles, you have got 2 poles in this system, and it is not difficult to see that the two poles are going to be on the right half plane. Right, that is where the two poles are, they are on the right half plane. Now, you want to know exactly where they are? Okay. So, you equate 1 minus S L by R double prime. This is not really a meaningful exercise, but just check it out. Is equal to 0 means S is equal to okay. And this is going to further simplify. Something like this. All right. So, if R double prime is equal to infinity, then this boils down to two poles at on the j omega axis. Okay. So, as long as you make sure that 1 by 2 L C is greater than minus 1 by 16 R double prime squared C squared. If you can make sure of this, then that will mean that you will have two poles which are complex conjugate pair which are in the right half plane. But if this inequality is not maintained, that is if 1 by 2 L C is no longer greater than 1 by 16 R prime squared C squared, then unfortunately the poles are going to start appearing on the real axis. Yes, you are going to get a pair of poles, but they will be on the real axis, which is not particularly exciting. Why? We will just come to it. So, this means that, just simplify a little bit more. Okay. all right. So, if r double prime is okay. All right. So, it is okay to have minus r double prime net negative, it is okay to have such a thing. However, what I am trying to say over here is you have to do it with some restriction. Now, what happens when I have two poles which are a complex conjugate pair of poles on the right half plane? What happens when they are on the right half plane, complex conjugate pair of poles on the right half plane? The impulse response of such a thing is, I do not know if you remember, it is a rising exponential modulated by a sine wave. Okay. So, this is what happens when the two poles are on the right half plane. Now, unfortunately, we can't have the output of our circuit rising forever, because you have got a limited power supply. Eventually, sooner or later, non-linearities of the transistor are going to come into effect. The system is not going to look like two poles on the right half plane anymore. As a result, the voltage waveform coming out of the circuit is going to be clipped at the power supply voltage. So, it is not going to look like a rising exponential. What it is going to look like is a clipped version of that, which is a square wave. Right? This is wonderful. Why is this wonderful? Lot of reasons. Number one, it solves this problem. Okay? I do not need 1 by Gm to be exactly equal to R parallel RDS. Number two, it solves this problem. The amplitude is the power supply voltage almost. Okay? I mean basically where the non-linearity is set in, that is the amplitude that you are going to get coming out of this circuit. Now, the additional benefit is that you are getting a square wave and not a sine wave. All right. Why do I like square waves? I think we talked about this before. We like square waves because the noise is only the phase noise. The amplitude noise is irrelevant because it is a square wave, right. Wherever there is any noise in the amplitude, it is cleaned out because you have got plus and minus VDD or the power and ground as your voltages. So, there is no noise as far as the amplitude is concerned, all the noise is in the phase of the signal, the zero crossing in the signal, which basically means, coming back from thermodynamics, statistical thermodynamics, that you get a 3 dB noise improvement over traditional sine wave signals. So, the noise in this noise power in a square wave is 3 dB less than the noise power in an equivalent sine wave. Wonderful. Okay, this is an extra benefit. All right. So, this is how we make oscillators. This is just one example of an oscillator. So, what I did was basically this. Now, of course, you do not like this because there is no control over how much power this is consuming. If you look at the DC picture, this voltage is at VDD, okay, which means you have got just one NMOS as a diode between VDD and ground. So, it is going to sink a lot of current. You do not really like that. You would want a current source over here to control how much current is going through the entire thing. That also gives you a handle to what is the GM of each of these individual MOSFETs, this particular current source, right. So, this is one example of an oscillator, tank based oscillator. There are variations in the topologies. You can use PMOSs, you can use NMOSs and PMOSs. For example, you could contemplate doing this. So, instead of using just a cross coupled pair of NMOS devices, I am going to use two inverters which are cross coupled. So, effectively this is what this is. So, that is why this is called a latch. Okay. If you redraw the circuit, you will find that this is exactly the same as what I have drawn over there. Anyway, so you can use this over here and then you can just put the inductor and capacitor right across. So, this also is quite popular, right, and in this case the negative resistance that you are getting is even better than before, because now you have the GM of the NMOS plus the GM of the PMOS, right. Of course, you also have the RDS of the NMOS and the RDS of the PMOS, but if that is not of concern compared to the resistance in the inductor, then this could be a potentially better topology. Anyway, so these kinds of topologies are used routinely. These are all tank based oscillators. In the next class, we are going to start talking about other kinds of oscillators which also use the tank circuit at its heart, Colpitt's oscillator, Pierce oscillator and so on. Okay. Thank you for your attention.